Hi, welcome to another lecture on linear algebra. Today we are going to talk about the rank of a matrix. Let's go ahead and see what this topic is about. So here we are going to talk about the rank of a matrix. What we have in mind is a coefficient matrix M, and then for this matrix we want to define something called the row rank, another thing called the column rank, and then generic rank of M, sometimes shown as a function rank followed by parentheses that contains the name of the matrix. So rank is a number, 0, 1, 2, 3 and so on. The coefficient matrix of a system gets to be labeled to have a certain rank. Let's go ahead first discuss what the general idea is, and then we go ahead and explain how to calculate it. I have written here three very simple linear systems. You notice the first one says x minus y equal to 2, and the second equation is 3x minus 3y is equal to 6. You look at this and notice something peculiar about this, which is the second equation is just a triple of the first equation. So whatever information was there, this being duplicated here. I'm not really being given any new information. So really I have one equation. In that case, we say rank of this coefficient matrix 1 minus 1 3 minus 3 is 1, reflecting the fact that we have essentially one equation. In this case, we have the second equation almost triple of the first one. All the coefficients on the left are triple of the coefficients here, and the right hand side doesn't follow suit. So this is of course a inconsistent system. It doesn't have any solutions. The rank still refers to the coefficient matrix on the left hand side. In some sense, you can say if I remove all the contradictory equations, how many will be left? Well, there's just going to be one equation left, either that or this one. So the rank of this coefficient matrix is also 1. Here's I have another linear system. This one, the second equation, has essentially nothing to do with the first one. It's not double of that, it's not a triple of this. Just a standalone by itself is something different from this. So I really have two different equations, and this left hand side, that other left hand side don't have anything to do with each other. In this case, I say rank of this matrix is 2, essentially saying there is nothing redundant here, there's no fat to be removed or anything, it's just a full rank. Okay, we need a definition that's going to work for us in bigger systems. 2 by 2 is nearly trivial, but as soon as the matrix gets any bigger, it becomes a subtle, rather complicated thing to understand. So let's go ahead, practice it in a couple of matrices. Again, these are two coefficient matrices. I'm not writing the x, y, z, t's anymore. Just have the numbers. This is numbers that supposedly show up on the left hand side of some equation, and we want to know what's the rank of this. What's the definition of this thing anyway? So general idea again is to isolate how many independent equations we could have in this situation like this. So what we do is that we are going to try to get the echelon form of this matrix. Then the number of rows that survive meaning they don't become just zeros across the board. The number of non-zero rows of that is going to be called the row rank of M. So row rank of a matrix is the number of non-zero rows of its echelon form. So let's write it first and then go ahead and practice it. So row rank of a matrix M is equal to the number of non-zero rows of echelon form of M. So how do we get echelon form? We can do by hand, or you can do with that software we talked about the other day. If the matrix is big, you use this one. If the matrix is small, you do it by hand. So let's go ahead and practice it in this case. So here let's go ahead and rewrite 1 minus 1 minus 1 2 2 minus 2 minus 1 3 minus 1 1 minus 1 and 0. So this is, let's call it row 1, row 2, row 3. And then we said we treat certain entries as pivots, certain other entries as targets, and then we go try to eliminate the bottom triangular portion of this rectangle, and that's going to give us our echelon form. Let me just remind you okay, so here are some example of row echelon forms. The number of leading zeros is supposed to increase as you go from one row to the next, and if the entire row of zeros is going to show up, it's going to be at the bottom. So you see you have one leading zero of 4 here and 5 here, and the next one is 6. So the number of leading zeros has to increase. Another convention is that they just put squares for leading entry. That means a first non-zero entry. These stars means so any arbitrary number here, doesn't matter what it is. And well, these are of course the zeros. So you see that the first non-zero entry is marching toward the right. Here you see it's marching toward the right here and here, same way. That's a row echelon form. So if we go ahead, whatever matrix they gave us, we perform this, and the number of rows that don't become identically 0, that's our rank. So rank of this will be 3. What would be the rank of this one? Look at that and tell me again the number of non-zero rows. So of course this is a 0 row, so you put that aside. So there are 3 rows left, so the rank of this is 3. Rank of this is 3. This is also rank is 3. How about the rank of this one? So this is squares with non-zero entries, and that makes the rank to be 3. This is also rank is 3. How about this? What is that? Well, if you said 2, you're in good company. Let's try one more time. What's the rank of this one? The rank, well, here's all the zeros at the bottom. You take that aside. Whatever is left, you see 2 rows left. So rank of this is 2. Rank of this one is 3. Rank of this one, well, all of them are so right. We have rank 5 in that. So the number of non-zero rows left is the rank. Okay, so that's the definition. We need to point out that regardless of how you come across your echelon form, the rank, the row rank is the same number. So even though 2 students can come across 2 different echelon forms out of the same matrix, the number of non-zero rows will be the same between their answers. We are not going to prove that right now. We're just going to accept it and move on, and perhaps later on we'll come back to that. So let's do this thing by hand, and then a second time around let's go do it by that software, so that we have practice on both end of it. Of course, this is a small matrix, so it is reasonable to expect us to do this thing by hand. So I'm going to go ahead, eliminate the 2. How do I eliminate it? It's a twice row, let's just write it in a standard way, row 2 minus 2 row 1. In order for me to be able to follow what I have written here, let me go label this thing a little bit different than before. So this is in our next round, a new R2. So let me write it. 1 minus 1 minus 1 2. This entry minus twice that entry becomes 0, and in this case this entry minus twice that entry, that accidentally becomes 0. This one becomes 1, and this becomes minus 1. And my row number 3, well, that's going to be the row I have here. If I just add to it row 1, what happens? What happens is this becomes 0, this becomes 0, this becomes minus 2, and this becomes 2. Okay, is this echelon? Well, not yet. The number of, well, this was supposed to be minus 2. Number of leading zeros is supposed to increase, or our leading entry is supposed to march toward right. So that means I have to take this as my pivot and eliminate that one. So how do I do that? So obviously I'm going to say this is row 3, but just to remember where it came from, let me call it row 3 prime, and then from that I have to add to row 2 prime. So that's going to be my final row number 3. So I'm putting primes to be able to track them later on. What do I get? Well, what I get is that I have 1 minus 1 minus 1 2, 0 0 1 minus 1, and of course the purpose of the last step is that we eliminate this entry, but accidentally the other one also eliminates. So first of all, what's the rank of this matrix? We go and count how many non-zero rows we have. Well, this one is of course row of entire zeros. This doesn't count, only 2 rows left. So we say rank is 2. Why? Because this is contributes, this one contributes, then this one doesn't. So rank becomes 2. Now you might feel a bit uneasy. Well, what does this mean? Rank is 2. What we are saying is that if you had an equation with this type of numbers on the left hand side, one of them could be written in terms of the other 2. That is, out of these 3 equations, one would be considered redundant. Just like in this case, this was a copy of that. This is a more sophisticated version of that you have 3, maybe you have 3 equations in front of you, but out of the 3 of them, one of them is redundant and only 2 of them can be considered independent. How do we see that? What is the dependence? So the word dependence and independence is going to come up in the next chapter, next section, but right now we can get a feel for it. Let's see what does this what happened here. So I am adding this row to twice that row, and all got wiped out. So R triple prime 3 became 0. Is that right? That's what this thing is. Well, let's go ahead and write it. R prime 3. R prime 3 is this one. Going back to the beginning. So we write for R prime 3. There's R3 and R1. Meaning the row that was here itself was some of these 2 rows. And then twice R prime 2. Well, R prime 2 itself was the row 2 minus 2 row 1. So I write 2 R2 minus 2 R1. So that is what R double prime 3 was really. And what happened to it? This became, let's make it kind of a, let's write it better. This is a vector that is 0, not just an ordinary 0. This is a vector that is 0, meaning this is 0 0 0 0, as many zeros as you want. This thing became a 0 vector. Let's clean this up. This means R3 plus R1 plus 2R2 minus 4R1 is 0. 0 means everything in it becomes 0. Let's clean this up. So this becomes minus 3r1 plus 2r2 plus r3 is equal to 0. Is that right? So minus 3r1 plus 2r2 plus r3 is equal to... What does this mean? Well, one way to interpret that is to say if you want r3, you can take this thing to the other side. That would be 3r1 minus 2r2. Is that so? Like if I take this, my original r3, the first thing that I had, minus 1, 1, minus 1, 0. This is my original r3. This is saying it is 3 times the row 1. Row 1 was 1, minus 1, minus 1, 2. That's my row 1. Minus twice r2. r2 was 2. Make sure I did not make a mistake here. This is 3r1. I'm supposed to made a mistake here. This was 3r1 minus 2r2. So let me write the multiples in black so it stands out. R2 is our second row here. 2 minus 2 minus 1, 3. So if I multiply this thing by 3, multiply this thing by minus 2, and add them up, I get the third one. Is that right? Well, 3 times 1 minus 2 times 2, or 3 minus 4 is minus 1, right? 3 times minus 1 minus 2 times minus 2 is a 4. So if you add minus 3 to 4, you get 1. That's right. 3 times minus 1 minus 2 times minus 1, so it becomes minus 3 plus 2, and that's minus 1. Finally, 3 times 2 minus 2 times 3 is actually 0, and that's what we see. So in this coefficient matrix, the third row can be created out of the other two by tripling this and subtracting double of that. Okay, still as matrix size is small, sometimes you can look at this thing and see the pattern right away if there is one. But as the size of the matrix increases, it becomes increasingly difficult to actually see what's going on. And the idea of this procedure comes out clearly. Rank of a matrix M is the number of non-zero rows of the echelon form of the matrix M. Okay, so number of non-zeros, well, you can actually count the rows that are non-zeros. You can count the number of pivots. You can count the number of leading elements. You can count the number of leading variables. Many different names could be used, but they are all doing the same thing. Okay, perhaps you go ahead and take the second matrix and calculate the coefficient matrix of that. But let me just show you again, as a matter of practice, how do we do this thing on that software. Well, it would be a good idea for us to practice this Gale software. So to search for this thing, you can search for Michael Iserman Gauss Elimination for it to come up for you. Okay, what did we say we do? We start by editing this thing. Our matrix is 3 by 4, so 3 by 4, I correct that, so it makes become 3 by 4. Then to enter these entries, okay, so this is excuse me, 1, and then we tap through, so -1, and again -1, and then 2, just tap 2, -2, -1, 3. So I'm just entering the numbers we had in the exercise we just did. The last one is 0. So again, you double check, make sure you did everything right. So hopefully I duplicated this set of numbers So I'm looking at my notes to make sure I am not going to go with a different set of numbers. Okay, so it looks like I entered my data correctly, and now I'm going to continue. So what do we do? Say resume. Okay, now we are ready to do Gaussian elimination. We said, well, all the arithmetic is taken off our hand. We just essentially playing a little simple video game here, if you wish to think about it, of a power-ups you collecting or shooting the enemy or something. So this is your gun and this is the target. So click on that and click on this. It eliminates it. Again, this is your gun or your pivot, and this is your target. There's nothing here for you to do. You come here, this is your next pivot. You use this to eliminate that one. And you notice the entire row got eliminated. Well, how many rows do you have left? Meaning rows that have non-zero entries in them. You have created the echelon form. When you have the echelon form, it's time to actually harvest this thing. You say, I have 2 rows that are non-zeros, and that's going to be my rank. Or count the number of leading entries. Here's a 1 and a 1. Or leading variables, again the same thing. You have only 2 of them. Now different students can have different echelon forms. Like for example, if you take this thing, add it to that one or subtract it, it's still echelon. So different students can have different echelon forms, but everybody agrees on the same thing, that there are exactly 2 rows that are non-zeros. That's going to be the rank. Okay, so that's what the rank of a matrix is. We typically talk about just the rank, but there are really 3 ideas. There is a row rank, there's a column rank, and then there is rank. Most often in the course we talk about row operations and row reduction and this and that, but everything we say about rows you could apply to columns as well. I mean, there's no really big difference between the 2 operations. So we can talk about the column rank of M. And then comes up a magical theorem in linear algebra, one of the first non-trivial, rather mesmerizing theorems in linear algebra, that these 2 ranks are the same. And the common value is just referred to as a rank of M, or written like in a function notation, rank followed by the name of your matrix in this. Okay, let me just give you a brief view of what this column rank is going to be. So we don't want to spend that much time on it. It's just the same thing we were doing with the rows, we can do with the columns. So one nice thing about this offer is that we can go to the very beginning, which was like this, and then we modified it to that one. Okay, so that's where we started. That is the coefficient matrix of this problem. So I went to the very beginning of this problem again. You remember we had this matrix here, and we started doing calculation of row rank, and we said 2 of them is enough to generate all the rest of them. Now how about the columns? So when it comes to columns, we can do one of 2 things. One thing is to play the same game that we were playing with the rows, we can do with the columns. With the rows, you were trying to create a row echelon. Row echelon means wipe out the lower entries of this matrix. Well, what do you think is going to be? Column echelon. Column echelon would be to wipe out the top of these matrices. Let's just go ahead and do it. So I'm going to use this as a pivot and try to wipe out these entries. Instead of the ones below it, I'm going to wipe out the ones in front of it. So this is a pivot, and I'm going to wipe this out. This is a pivot, I'm going to wipe this one out. This is a pivot, and I'm going to wipe this one out. Okay, now I want to come to this location, but this entry has become 0, so I have to switch with one of the next ones. So I go ahead, swap the two columns. Previously we were talking about swapping rows. You can swap columns, so I can swap this column with this column. You notice what happened? The numbers exchanged. So now I can use this entry as my pivot and wipe the entries in front of it. So here's what I do. You notice now two columns are entirely wiped out, and we have only two non-zero columns left. So that's going to be called the column rank of the original matrix. Only two columns survived, the rest got wiped out. What that theorem says is that it's not accidental that we had two rows left and then two columns left. That always happens. As I said, it's rather magical. It's not trivial. Why would such a thing happen? But the row rank and the column rank, both of them are same number, and the common value is referred to as just rank. So when we talk about the rank of a matrix, you might have gone after row rank and calculated it, or maybe perhaps you went after a column rank and you calculated it's the same thing. You can notice that issue in this tiny matrix. You notice that this row and this row are related to each other. The second is triple of the first row. Is that right? How about the columns? This first column is 1, 3. Second column is -1, -3. Are the two columns related to each other? Obviously so. This is a -1 times that same is here. So second column can be made out of the first column, or same way second row can be made out of the first row. Okay, so we have the following. Let's repeat. The rank of a matrix mem is the number of non-zero rows of the echelon form of M. Of course, if you have row reduced echelon form, that's even better, but that's going to have the same answer. And instead of rows, we said we can use the concept of columns, and the whole thing is recorded eventually as just the rank of a matrix. Okay, we are going to keep this conversation short. There's just one more thing I mentioned here. You remember that when we were talking about solving equation, we had another terminology as well, and that terminology was with respect to free variables. So we had these leading entries or leading ones, and whatever column that was left. So for example, if this was X and Y and Z and say W, X and Z were labeled as leading variables, and the Y and W were sometimes referred to as the free variables. So since I'm counting these for the number of non-zero rows, I can do another style of counting. I can count all the columns I have or all the variables I have, and from that subtract the number of free variables. That will also give me the rank. So another idea of a rank is that rank is same as the number of columns you have, or the number of variables, total number of variables you have, minus number of free variables. So rank of a matrix, you can write it as the number of columns or number of variables you have minus number of the free variables you have. Okay, so you practice that in a few questions that we are going to have related to this, and then we are going to move on to other topics. Until next lecture, good luck and God bless.